These are the step-by-step solutions to the 2011 AP Chemistry test. You can go to collegeboard.com to look up the questions. Question number 1. You're given 3 beakers. Beaker 1 has 0.1 molar HCl, Beaker 2 has 0.1 molar NH3, and Beaker 3 has 0.1 molar NH4Cl. Part A. HCl, hydrochloric acid, is a strong acid. What that means is that it will dissociate completely into H plus and Cl minus. So the H plus concentration is just equal to the HCl concentration, which is equal to 0.100 molar. The pH is defined as the negative log of the H plus concentration, so it comes out to be 1.000. Part B. Ammonia is a weak base, so when ammonia is dissolved in water, it undergoes this equilibrium NH3 plus H2O going to NH4 plus and OH minus. The Kb is the equilibrium constant for this base hydrolysis equilibrium. So it's equal to the product of the concentration of the products divided by the concentration of the reactants, except water is a pure liquid, so its concentration is not included. So Kb is equal to the NH4 plus concentration multiplied by the OH minus concentration divided by the NH3 concentration. Part 2. To calculate the OH minus concentration of a weak base solution, you need to do an ICE calculation. So we'll set up the ICE table. The initial concentration of the NH3 is 0.100 molar as specified by the problem, and the concentration of the NH4 plus and the OH minus are both 0. The stoichiometry is 1 to 1 to 1, so the change in the concentration of the NH3 is minus X, while on the product side is equal to plus X and plus X for the NH4 plus and OH minus. So applying the changes to the initial, we get 0.100 minus X for the NH3 concentration and X for both the equilibrium concentration of NH4 plus and OH minus. Now we put these back into the Kb expression. The problem gives the value of Kb as 1.8 times 10 to the minus 5. We put the equilibrium concentrations from the last row of the IC table back into Kb. We get x squared over 0.100 minus x. We know that this is a weak base, so the amount of change in the concentration for the NH3 is going to be weak. So we assume that x is much smaller than 0.100, and the expression for Kb becomes approximately x squared divided by 0.100. And from this we can actually calculate what x is, and it turns out to be approximately equal to 1.3 times 10 to the minus 3. And we see that the OH minus concentration is just equal to x, so the OH minus concentration is 1.3 times 10 to the minus 3 molar. C, part 1. We know from part B, the Kb for NH3 is equal to 1.8 times 10 to the minus 5. And the Ka for its conjugate acid, which is NH4 plus, then must equal to Kw divided by Kb for NH3. And so the value for Kw is 10 to the minus 14. Kb is 1.8 times 10 to the minus 5. So Ka for NH4 plus comes up to be 5.6 times 10 to the minus 10. In part 2, we need to do an IC calculation, but in the mixture we'll have both NH4 plus and NH3 present. So to do this, we need to know the initial concentration of both of them. Beaker 2 contains 0.100 molar NH3. Multiplying that by the volume, which is 0.0250 liter, will give us a number of moles of NH3. And we can do the same to obtain the number of moles of the NH4 plus that was originally in beaker 3. After having the number of moles, we need to know the total volume in order to calculate the initial concentrations that would go into the ICE table. The two solutions, when they're mixed, the total volume is twice as much as the individual solutions previously, so the initial concentrations will be diluted by a factor of 2. Or you can simply take the number of moles of each and divide by the total volume, which is now equal to 0.0500 liter. And again, we write down the equilibrium. In this case, is NH4 plus H2O going to NH3 plus H3O plus. And we put in the initial concentration into the first row of the ICE table. Again, the stoichiometry is such that the change would be minus x on the left side and plus x for the right side. So applying the changes to the initial, we get 0.0500 minus x for the NH4 plus concentration, and for the NH3 concentration, we get 0.0500 plus x, and for the H3O plus, we get x. Now we'll put these concentrations back into the Ka expression. The Ka is equal to NH3 concentration multiplied by H3O plus concentration divided by the NH4 plus concentration. And as we found in part 1, the value for Ka is 5.6 times 10 to the minus 10. So now we put the equilibrium concentrations in, and we get 0.0500 plus x, all multiplied by x on top. And in the bottom, we get 0.0500 minus x. Again, we use the approximation that x is much smaller than 0.0500, so in the numerator we end up with 0.0500 multiplied by x, and in the denominator we have 0.0500. Now they cancel out from both top and bottom and leave x. So x is just equal to the value of Ka, which is 5.6 times 10 to the minus 10. And we see that the H3O plus concentration is really just equals to x. So the pH is negative log of the H3O plus concentration, which comes out to be 9.25. D, part 1. So we have the mixture that comes from part C, and we are going to add the content of beaker 1 to that. Before we added the content of beaker 1, we can figure out the number of moles of NH4 plus and NH3 in the beaker. And we've done that in part C, so the number of moles of each of these I'm going to plot on a graph. On the left side, we have the NH4 plus number of moles. On the right side, we have NH3, and we saw that both of them are 2.5 times 10 to the minus 3. And beaker 1 contains a strong acid, so what that does is that it would protonate the base, in this case is NH3, and turn all of it into NH4 plus. We've calculated the number of moles of the H plus, and that is given by the volume multiplied by the concentration. So the number of moles of H plus from beaker 1 is equal to 2.5 times 10 to the minus 3 also. And what that would do is to convert the same number of moles of NH3 to NH4 plus. And we see that we originally have 2.5 times 10 to the minus 3 moles of NH3. So all of that is going to be converted into NH4 plus, so that now the total of the number of moles of the NH4 plus becomes 5.0 times 10 to the minus 3, and then we have nothing left in the NH3. In order to have a buffer, you must have plenty of a weak acid and plenty of its conjugate base present in the solution. You see that in this case, the solution has a lot of NH4+, but virtually no NH3. So this is not going to be a good buffer. So finally, to calculate the NH4+ concentration, we need to take the number of moles of NH4+, which is what we see in the chart, and divide this by the total volume of the new solution. The total volume is going to be the extra volume from beaker 1, which is 25.0 milliliters, plus the total volume from the solution in part C, which we have already found is 50.0 milliliters. So the total volume is going to be 75.0 milliliters. And from the number of moles of NH4+, which is 5.0 times 10 to the minus 3, you divide that by the volume, which is 0.0750 liter, and you can calculate the concentration of the NH4+, which is 0.0667 molar. Since NH4+ is a weak acid, you might have to carry out an ICE calculation to calculate the final equilibrium concentrations. But because the Ka value for NH4+ is so small, you'll find that even if you had to carry out an IC calculation, the concentration of the NH4+ at equilibrium is really just approximately equal to 0.0667 molar, just as we have calculated. Number 2. In this problem, you're given 16 molar HNO3 solution, 2 100 milliliter graduated cylinders, a 100 milliliter beaker, and goggles, gloves, stirring rod, and distilled water. So in part A, number 1, the number of moles of HNO3 is equal to the volume multiplied by the concentration. So if you want 50 mil of 6 molar HNO3, you take the volume, which is 0.050 liter, multiply that by 6 molar, you get 0.3 moles. And that number of moles must equal to the original volume multiplied by the original concentration. So the volume will come up to be the number of moles divided by the original concentration, and that is equal to 0.019 liter, which is 19 milliliters. So to prepare 50 milliliters of 6 molar HNO3, we need to mix the 19 milliliters of 16 molar HNO3 with enough water to make a total of 50 milliliters of solution. So to do that, first we would put on our protective equipment, goggles and gloves. Number 2, we will measure out 19 milliliters of 16 molar HNO3 in one graduated cylinder. Then we will measure out 31 milliliters of distilled water in another cylinder. The two volumes together will give me a total of 50 milliliters. Then we'll put H2O from the second cylinder into the beaker. Finally, we will mix in the HNO3 from the first cylinder, and then we can stir. Some students would answer that after step 2, you can pour enough water into the first cylinder to make the total volume come out to be 50 milliliters. Well, that formally is correct and will give you a solution at the right concentration. Putting water into concentrated acid is not a good practice because it might splash, so that is not the preferred answer. And also at the end you'll still have to make sure that it's well mixed, so even with that you'll still have to pour it into a beaker and then stir. Notice that the precision of the volume that you need, you only need two significant figures. You need 19 milliliter, and a graduated cylinder calibrated to within plus or minus 1 milliliter should have enough precision to measure out this volume with two sig figs, so you do not need a volumetric flask. Part 4. Any acid spill should be handled by neutralizing it with a base. NaHCO3 should be used because the HCO3 minus ion is weakly basic. The mass of the precipitate can be obtained by taking the total mass and subtracting from it the mass of the crucible. The total mass at the end is equal to 29.2598 grams, and the mass of the crucible alone is equal to 28.7210 grams. We'll take the net mass, which is 0.5388, and we'll have to divide it by the molar mass of AgCl. And the molar mass of AgCl comes out to be 143.32 grams per mole. So the number of moles of AgCl comes out to be equal to 0.003759 mole. So we have the number of moles of AgCl, but the alloy only contains silver and another metal. So what we need to do is to take the number of moles of the AgCl and find out what is the mass of the Ag alone. Of course, the mass of the silver is just equal to the number of moles we just calculated, multiplied by the molar mass of silver alone, and that comes out to be equal to 0.4055 gram. And now the mass percentage of the silver is equal to this mass divided by the total mass of the alloy, which the problem indicates is 0.6489 gram, and we'll multiply that by 100%. And that comes out to be 62.49%. Number 3, Part A. To calculate the delta H of the reaction, we can make use of the delta H of formation of each of the reactants and products. We take the sum of the delta H of formation of all the products and subtract from that the delta H of formation of all the reactants. The product is H2O liquid, and we have 2 of that. The reactants are O2 and 2H2. The delta H of formation of H2O liquid is given and is equal to negative 285.8 kilojoules per mole. The delta H of formation of O2 and H2 are both 0 because they're both elements in their most stable states, and by definition the delta H of formation is 0. And putting this all together, delta H for this reaction is equal to minus 571.6 kilojoules per mole. The amount of heat released is proportional to the number of moles of reaction that has taken place. And to calculate that, we can use the number of moles of H2. We know that there are 10 grams of H2 that is being used, and dividing that by the molar mass of H2, which is 2.016 grams per mole, we get 4.96 moles of H2 has been consumed. But since the reaction uses 2 moles of H2 for every mole of the reaction, the number of moles of reaction that has actually taken place is 4.96 divided by 2, which is 2.84 moles. And now we take that and multiply that by the amount of heat that is released per mole of reaction, and at the end we get 1.42 times 10 to the 3 kilojoules of heat. C, you're given the delta H of vaporization of liquid H2O. That is the delta H of the reaction H2O liquid going into H2O gas, and that's given as plus 44.0 kilojoules. And we have the delta H for the reaction above. We need to add these 2 equations together in order to eliminate the liquid H2O from the reaction, so that at the end we get gaseous H2O as a product. But to do that, you see that in the second reaction we actually have 2 H2O liquid on the left. So in order to eliminate that, we must take the first reaction and multiply that by twice in order to be able to cancel out the 2 liquid H2O. So we will do that, but we will also need to multiply the delta H of the first reaction by a factor of 2. So now adding the two equations, we see that we get the correct overall reaction, but we also have to add up the two delta H's. So delta H for this reaction is equal to negative 483.6 kilojoules per mole. You're given the two half reactions that are actually involved in the overall reaction. The first one is 2H2O liquid plus O2 gas plus 4 electrons going to 4OH minus with a half cell potential of 0.40 volt. The second one is 2H2O liquid plus 2 electrons going to H2 gas plus 2OH minus with a voltage of negative 0.83 volt. Now, in order to get an overall reaction that consumes H2 gas, what you need to do is to flip the second half reaction around to get a oxidation half reaction. So we'll do that, and then that turns out to be H2 gas plus 2OH minus going to 2H2O liquid plus 2 electrons. And that has now a cell voltage that is positive 0.83 volt. And we see that now we have in the first equation a reduction half reaction, and the third line we have a oxidation half reaction. But you see that the first step uses 4 electrons, but the second one uses only 2. So to balance out the number of electrons that are exchanged in this redox reaction, we must multiply the second by 2. And doing that gives me 2H2 plus 4OH minus going to 4H2O and 4 electrons. And now the number of electrons are balanced, and we can add the 2 and cancel out everything that's common on both sides. And the overall reaction turns out to be 2H2 gas plus O2 gas going to 2H2O liquid, which is exactly the same reaction we got in the problem. Now, in order to get the overall cell voltage, what we need to do is to add up the reduction half potential with the oxidation half potential. Now notice that even though we have multiplied the oxidation half reaction by twice to get the right stoichiometry, we do not have to multiply the half cell potential. So you will just take the second reaction, and this half potential is unmodified, which is still 0.83 volts. And adding these two will give you an overall cell potential of 1.23 volts. F part 1. We know that for every mole of reaction, 4 moles of electrons are involved. We know the number of moles of hydrogen from the problem, so we actually want to determine the number of moles of electrons corresponding to that. But for every mole of reaction, only 2 moles of hydrogens are involved. So if we want to calculate the number of moles of electrons, we need to take into account the stoichiometry. 4 moles of electrons for every 2 moles of H2 used in the reaction, multiplied by the number of moles of H2 used, will come out to be 1.9 mole. And 2, the current is defined as the amount of charge that is passed through the circuit divided by the time. The total charge is equal to the number of moles of electrons, which we calculated above, multiplied by the charge per mole of electron, which is called the Faraday's constant. We take 1.9 mole of electrons from part 1. We multiply it by the Faraday's constant, which is 96,485 coulombs per mole. And we divide by the total time, which the problem gives us as 600 seconds. And the total current turns out to be 3.0 times 10 to the 2 amps. According to the reaction specified in the problem in part G, using butane gas in the fuel cell actually produces CO2, which is a greenhouse gas. But using the fuel cell with H2 as the input produces only water, which is a clean product, so using H2 is to be preferred. The problem specifies that you have a reaction between magnesium hydroxide and hydrobromic acid. Magnesium hydroxide is an insoluble salt, and its formula is MgOH2. Hydrobromic acid is a strong acid, so in a solution, essentially you have HBr dissociating completely into H plus and Br minus. The reaction is an acid-base reaction where the acidic hydrobromic acid is neutralizing the basic MgOH2 solid. To react with 0.10 mole of magnesium hydroxide, according to the stoichiometry, you'll need twice the number of moles in H+, so you need 0.2 moles of H+. And the number of moles is equal to the volume multiplied by the concentration. So if you need 0.2 moles and the concentration is 2.00 molar, then the volume will turn out to be 0.20 mole divided by 2.00 molar, which is 0.10 liter, and that is equal to 100 milliliters. Part B. This is a complex ion formation reaction. So you have a soluble solution of cobalt 2 plus ion, and so the reaction is between cobalt 2 plus and the chloride forming a complex ion. The most common complex ion between cobalt 2 plus and chloride minus is actually CoCl4. That is one cobalt 2 plus with 4 chloride ions. And so if you count up the total charge of this complex is equal to 2 minus. If you didn't know that the most common ion between cobalt 2 plus and chloride contains 4 ligands, if you had put down anything between 1 and 6 for the complex of the cobalt 2 plus with the chloride, your answer would have been counted correct. Part 2. A Lewis base is essentially a lone pair donor, and so in this case, to form this complex ion, each of the 4 ligands, the Cl- ion, is acting as a Lewis base. C, Part 1. You have a reaction between copper metal and a silver solution. The reaction is a redox reaction in which the copper is being oxidized and the silver plus is being reduced. Copper, when it is fully oxidized, becomes copper 2 plus, and silver plus, when it is fully reduced, becomes metallic silver. And to balance the charge, you will have to have 2 Ag plus on the left and also 2 Ag on the right. During the reaction, obviously the reactants are being consumed and the products are being created. So you should see metallic copper go away, and you should also see metallic silver plated out. Number 5, Part A. The arrangement of the atoms in this molecule is shown here. And you notice that nitrogen is a group 5 element, so therefore it should have 5 valence electrons. On the other hand, each hydrogen has only 1 electron, but a hydrogen needs only 2 electrons to complete its valence shell, but nitrogen needs 8. So to satisfy its valence, nitrogen would need to form 3 bonds, and each hydrogen will need to form only 1 bond. And the easiest way to make this happen is to form a single bond between the 2 nitrogen atoms, and then each of the nitrogen is going to form a single bond with the other 2 hydrogen atom on each side, and finally there's a lone pair on each nitrogen atom. B, the answer is no, this molecule cannot be a planar molecule. The reason is, according to VSEPR, the geometry around each N atom, because there are 4 electron pairs around the nitrogen, should have a tetrahedral geometry. And because of that, the molecule cannot be a planar molecule. C. The structure of the C2H6 molecule is like this. This molecule has 2 carbons bonded to each other, and we also have 3 hydrogens around each carbon. So the molecule is completely symmetric, and therefore it is not polar. But the N2H4 molecule, because it is asymmetric, is actually polar. So because of that, the intermolecular force that acts between the polar N2H4 molecules is stronger than between the nonpolar C2H6 molecules. And because of this, this leads to a higher boiling point in N2H4. D. Because of the presence of the lone pair on each nitrogen in the N2H4 molecule, it is actually basic because the lone pair can bind the proton according to this reaction. And so because of this, a solution of N2H4 is basic. In this reaction, N2H4 plus O2 going to N2 plus 2H2O. If you work out the oxidation state of each of the elements in the reaction, you see that some of the oxidation states have changed. On the reactant side, because O2 is in an element by itself, the O atoms in this O2 molecule each has oxidation state equals to 0. But on the right-hand side, you see that O is bonded with hydrogen to form a compound, and we know that when O forms a compound with other elements, its oxidation state is -2. Similarly, you see that the nitrogen atoms on the product side, because the 2 nitrogen atoms are in a element N2, each of the oxidation state is equal to 0. But on the left-hand side, we know that the 2 N atoms are bonded to 4 hydrogen atoms in the compound N2H4, and each hydrogen is +1, so the 2 N atoms on the left-hand side in the molecule N2H4 must have an oxidation state that is not equal to 0. And since the oxidation states have changed, this reaction must be a redox reaction. F. We see that in this reaction, on the reactant side on the left, we have a total of 2 moles of gases, but on the right-hand side, we have a total of 3 moles of gases. And because of this, the entropy of the reaction must increase because we go from 2 to 3 moles of gases. G. It is incorrect to say that the delta H of this reaction being exothermic is due to the bonds being broken. The reason is because breaking bonds actually requires energy to be put into the reaction. So therefore, this must not be the reason why energy is released by this reaction. Number 6, part A. The vapor pressure of a liquid is the partial pressure of the vapor that is in equilibrium with the liquid. The problem states that at 35 degrees Celsius, the vapor pressure of ethanol is equal to 100 torrs. Therefore, if there is nothing else in the chamber other than the liquid ethanol and the vapor above it, the pressure of the vapor should exactly equal to 100 torr. Part B. There are primarily 2 reasons for this. First of all, at a higher temperature, at 45 degrees Celsius, the temperature is higher and hence the molecules are traveling faster. And this increases the pressure as the molecules impinge on the walls of the container. The second reason is that at higher temperature, the ethanol molecules in the liquid could actually escape more easily from the liquid because they're traveling faster into the vapor. So this would lead to a higher vapor pressure. C, part 1. For a zero-order reaction, a plot of the concentration versus time should give a straight line. But for a first-order reaction, a plot of the log of the concentration versus time should give a straight line. On the other hand, for a second-order reaction, 1 over the concentration versus time should give you a straight line. So if you look at the three plots, these are plots of concentrations versus time, 1 over concentration versus time, and log of the concentration versus time. And so whichever gives you a straight line should then indicate what order the reaction has. And you see that the first plot, which is concentration versus time, is a straight line, so the reaction should be zero order. The rate law indicates that the rate is equal to the rate constant K multiplied by the concentration of the reactant to the order. In this case, the order is 0, and anything to 0 order is just a constant, so the rate is actually just equal to the rate constant itself, which is K. And to calculate the value of the rate constant, you can measure the rate because, according to part 2, the rate is just equal to K. And the rate is defined as the negative change in the concentration of the reactant divided by the time elapsed. And to get the rate easily, we can take the first and the last point on the first graph. The concentration at the end is 0.0020. The concentration at the beginning of the reaction is 0.0100. And we would take the difference of those two and divide by the time difference, which is 2000 at the end and 0 second at the beginning, but there is an overall negative sign. The number comes out to be 4.0 times 10 to the minus 6, and that is in units of molar per second, and so that should be the value of K itself. In this reaction, you have the decomposition of one molecule, CH3CH2OH, into two molecules, CH3CHO and H2, and both of them are gases. And according to the ideal gas law, we know that the pressure should be proportional to the number of moles. We started with 1 mole of reactant with a pressure of 0.4 atmosphere, and we ended up with 2 moles, so at the end the pressure should be equal to 0.80 atmosphere.